The views expressed in this podcast or on www.constellationspodcast.com do not officially represent the views of the U.S. military or the United States government. The appearance of U.S. Department of Defense, DoD, visual information does not imply or constitute DoD endorsement.
Welcome to Constellations, the podcast from Kratos, where industry leaders share their thoughts and experience on the future of space business, policy, and opportunity. If you like Constellations, please support us by giving a rating and review on iTunes. And don't forget to share this podcast online to help our community grow.
Welcome to Constellations, the podcast from Kratos. My name is John Gilroy, and I'll be your moderator. Today we have three guests. We have Lieutenant Colonel Gary Thompson, Spectrum Warfare Division, Space Systems Command, U.S. Space Force. Ben Hilburn, Head of Strategic Initiatives, Azure Spectrum Technologies at Microsoft. And Stuart Daughtridge, Chairman, Digital Intermediate Frequency Interoperability Consortium, or for us mere mortals, just DIFI. Our guests are here to discuss needs and challenges associated with interoperability and how industry can support the digital transformation of space, satellite, and related industries. First of all, let me introduce our guests. Lieutenant Colonel Gary Thompson is a space systems architect with the U.S. Space Force. He advises and assists on matters concerning business practices and technologies to advance U.S. government commercial and coalition partner satellite communications capabilities as an integrated enterprise. And that's the key word, integrated enterprise. Mr. Benjamin Hilburn is head of strategic initiatives on the Azure Spectrum Technologies team at Microsoft, where he is working on new topics in software radio and wireless on the cloud, including 5G, cloud-borne RF sensing, and virtualized satellite communications. Mr. Stuart Daughtridge is director and chair of DIFI. He has been in the satellite and aerospace industry since 1986. His current position, he leads Kratos' satellite ground segment technology research and development efforts. Okay, we're going to start with the Lieutenant Colonel. Lieutenant Colonel Thompson, it seems there's a growing desire for the U.S. military and commercial satellite ground system to be able to operate together in a coordinated way. So what's driving this? What's pushing this deep?
Well, thank you, sir, for having me on today. As they say, a long-time listener, first-time caller. So I appreciate this opportunity and this question, because this need is being driven from many factors, including our operational needs for mission assurance and budgetary efficiencies that can stem from more effective use of available ground assets. Ground is a critical component of the end-to-end communications that U.S. forces and our allies rely on to perform their missions each day. Many of the SATCOM services include connections to ground sites, which act as gateways to move data across terrestrial links to destinations worldwide. Unfortunately, how we plan to end this end-to-end connection is often closed and inflexible in nature. Breaking this paradigm is important to ensure the next level of flexibility, which is the ability to transition between military and commercial space and ground systems independently and at the speed of need. This is a hard problem due to the way that many of these connections are currently developed, procured, planned, and operated.
Lieutenant Colonel Thompson, standards often form the basis for the introduction of new technologies and innovations and ensure that products, components, and services supplied by different companies will be mutually compatible. So what role do you see open standards filling in making commercial and military ground systems more interoperable?
Another great question. The standards are the foundation for disciplined systems engineering to go after the hard problems that I mentioned earlier. Standards are a key tenet of MOSA, or a modular open systems architecture, which is a priority here at Space Systems Architect, to enact guardrails to guide our programs to be more interoperable. This also helps to prevent vendor lock when we apply the MOSA principles to the right level of our architecture. We need to be able to bring in the best intellectual property and capabilities. And in order to do this, we need to develop standardized interfaces at our portfolio level. The portfolio level architecture is where we map force design architectures to lower level program or implementation architectures to meet our desired mission capability. These standards need to be open and consensus-based to truly reach MOSA ideals. Our Space Systems Architect Engineering Office has been participating in several consortia and groups to mature our approach for enterprise portfolio management. We are working with industry to incorporate best practices while minimizing the amount of changes needed in existing product lines and facilitating the evolution of new and existing product lines towards greater compliance with our interface standards.
I want to continue this a little bit further here. Lieutenant Colonel Thompson, would simply complying with framework standards such as VITA 49 guarantee interoperability between a military and commercial satellite ground system? Is that enough?
VITA 49 plays an essential part in standardizing the underlying plumbing for interoperability at the IF transport layer. But interoperability at the data and application layers must also be built in. For this reason, as Space Systems Command, we're working on flexible networking, cross-mission, and interoperability standards to build on VITA 49 and DIFI in order to enable interoperability between military and commercial ground networks. What we envision are user networks that can be easily moved between different ground antenna sites operated by different service providers. Our SATCOM capabilities rely on a significant number of heritage systems. So applying middleware overlays can help us move towards data fusion sooner rather than waiting for a complete recapitalization of our terminals, space systems, and ground segments. This approach allows us to harvest interoperability sooner and reach higher levels of mission assurance now. But these are predicated on having defined standards and interfaces. This also requires a retooling on how we plan and monitor these systems in providing their end-to-end connectivity. Over the past couple of years, we've done several demonstrations and have advanced standards for flexible terminals and SATCOM networking. In each demonstration, we were able to show a significant increase in our ability to detect where and why the end-to-end link broke and quickly restore to an alternate path. This knowledge and having each appliance in the end-to-end connection become a sensor providing critical data on the status of the mission traffic is an important step to providing the user at the edge with the information they need to keep their link active. This can't work if we treat each end-to-end connection as a single connection to move our data. Having standards which enable us to quickly reroute our data over the full inventory of government and commercial space and ground service providers is a revolutionary advancement in our delivery of SATCOM services.
Hey, Ben, the Lieutenant Colonel just used the phrase application layer, so it's natural and logical for me to toss over to you at Microsoft. So, Ben, should open standards be applied to all elements of a satellite ground system, or are there certain areas where mandating standards could actually hinder competition and innovation?
Yeah, that's a really interesting question. So there's a lot of benefits to open standards and interoperability standards, but for the context of this question, I think it's useful to think of two major ones. So one is making technical development easier, right? So let's pick an example. PCI Express, right? PCI Express is a standard way of moving around data. It exists not only in your big computers, but in like cabled connections to phones, right? Actually look a lot like PCI Express connections, right? But in a lot of cases, that's at the level that's transparent to the larger system or a customer, right? For the most part, when you go to build some compute capability, you're not worried about what version of the PCI Express bus is sitting in that thing, right? But what's not transparent, right? And a second major benefit is in driving interoperability at the systems level, right? So there we start to think of things like, where is it useful to disaggregate a system? And by that, I mean, if you think of, let's think of a satellite radio system, for example, where you have some higher level processing, perhaps application level processing, you've got some radio processing, and you have a radio unit, right? Is there value in that entire chain being from a single vendor, monolithic, right, and completely one thing that's inseparable, right? Or is there more value in disaggregating it such that you're able to, pick the pieces from the vendors that are providing the best products along the way, right? And there's all kinds of additional benefits that come along with that, right? If in a disaggregated system, you were able to, for example, upgrade the radio, right, without changing the rest of the chain, right, which allows you to do things like accelerate your acquisition cycle, right? It allows you to accelerate your development cycle as you're building new capabilities, right? Because you don't have to think about the entirety of the system. So I think the question comes down to, okay, where can we use standards like this to drive innovation, and where is the line for where it hinders competition? And so I really think it comes down to It's different from system to system, but I really think it comes down to what is transparent to a system integrator or an operator, and where does it drive value for them to benefit from these interoperable disaggregated systems. And I think that's kind of the dividing line that defines where you're hindering competition if you go further, right? Because you do want to allow vendors to be able to build their differentiated IP within a block and monetize that.
Gentlemen, thousands of people from all over the world have listened to this podcast. Go to Google and type in Constellations Podcast to get to our show notes page. Here, you can get transcripts for all 100 plus interviews. Also, you can sign up for free email notifications for future episodes. You know, Ben, both you and the Lieutenant Colonel use this word interoperability, and that's kind of the focus of the whole discussion today. So in an ideal world, so what are the ideal use cases for interoperability standards? I mean, can you share an example of a successful application of an interoperable standard?
Oh, yeah, sure. A great example of a successful use of an interoperable standard is Ethernet, right? Perhaps, one of the most widely used interoperable standards. Ethernet doesn't care what's on either end of a link. It doesn't even care if it's wired or wireless, right? Ethernet has created tremendous opportunity for innovation and technology advancement. And so I think that's a really strong example of it focused on creating a standard way for moving and understanding data such that people building products or components that sit on either end of an Ethernet link, right, could differentiate on what you do with that data, and not having to worry that they're not going to understand the data when they get it, right? Taking perhaps a more recent example, right, that's been around for a while, I'd point to the 5G community, ORAN, right? So ORAN is short for Open RAN or Open Radio Access Networks, right? And the short story there is in previous generations of cellular, the cellular operators were buying monolithic systems from the equipment providers, right? So kind of going back to the example in the previous question you asked me, John, they have to buy the radio and the modem and the processing all from a single vendor, right? And that was really limiting what the operators could do. It was limiting acquiring new systems, upgrading systems, right? It introduced additional complexity in the maintenance of systems. And they kind of, as they were putting together 5G, there was kind of this industry-wide, we're tired of this. This doesn't make sense anymore. We need an interoperable standard so that we can, just buy a radio unit from the company that builds the best radio for my specific purpose, and buy the processing from a different company that builds the best processing for my specific purpose, right? And that industry has really rallied around ORAN and is fundamentally shaping the direction of 5G and its use both commercially and in government. I think it's another great example of successful application of interoperable standards.
Hey, Ben, when I was doing show prep for this interview, I came across VITA 49. And at first I thought it was a vitamin.
Oh, yeah.
No, it's not a vitamin. So maybe people are listening, wait, is it a vitamin show? No, it's nothing to do with vitamin. So what exactly is VITA 49 and what's its relationship to DIFI here?
Ooh, okay. So VITA 49 or VITA 49, I'm actually not sure what they prefer. I hear it both ways. I use VITA though. So VITA 49, it's often thought of as a standard interface. That's not really quite accurate though. VITA 49 is more like a framework for building interfaces. It kind of got this bad rap because lots of different vendors would produce equipment that they claimed was compliant with VITA 49, and none of them would work together, right? Which kind of breaks the promise of interoperable standards. But the problem is that VITA 49 is not a specific interface. VITA 49 is a way of creating interfaces, right? So what ended up happening is every different vendor was indeed creating a VITA 49 based interface, but they all look different, right? And so you'd end up, you'd have a customer that would buy some piece of processing that ingested VITA 49 and some piece of hardware that produced VITA 49, and they couldn't work together. And that actually is exactly where DIFI lands. So DIFI is based on VITA 49. It is you could think of it as a VITA 49 schema. So it is a specific implementation of a VITA 49 interface designed to support virtualized satellite communications on the ground, in the ground segment, right? And so it allows us to benefit and leverage a really broad ecosystem of VITA 49-based technology and IP and vendors that already exist, because VITA 49 has been around for a while, right? But then create something that is specific and solves interoperability in the ground segment for virtualized communications in a way that I think is going to be really impactful.
Speaking of frameworks, I want to put a framework on this answer. So the VITA 49 has really been around since the early 2000s, and DIFI is really relatively new, isn't it?
Yeah, that's right. And we, Stuart could actually probably has better memory than I. Stuart, when was the first board meeting for DIFI? Was that 2 months ago? It's really recent.
It was in August.
It's November now, so 3 months, but yes.
Yeah.
Well, Ben, that was a great toss. Now I've got a couple questions for Stuart here. So, Stuart, you are the chairman. So what exactly is the status of the DIFI organization?
So the DIFI organization was, if we just discussed, was established and published its 1.0 version of the specification in, end of August timeframe. And since then, the response from the industry has been fantastic. We've had steady growth in membership with several new members joining every week. We've had excellent support from the US DoD. But more importantly, considering that it's a standard, what really counts is, all we have is a document until it's adopted. And from an adoption point of view, we've had steady downloads of the specification from our website by over 60 different organizations. The 1.0 specification has already been made a requirement in a recent Army RFI. So really excited about that. And now we're starting to up our working groups to start the management of the standard itself and to consider new standards that would help the industry go through a digital transformation. And lastly, in the near future, we're going to be starting up working groups about how we do certification against the standard. So we hope to be able to provide a free certification capability to the industry for self-certification, along with a third-party certification program.
Stuart, when we were talking to Ben, we mentioned the VITA 49 and been around for a while. So maybe DIFI will be around for a while. So what are your long-term goals for the organization?
Yeah, so the reason we formed the organization was really to help enable the digital transformation of the satellite industry. The satellite industry has, the first step in that digital transformation is really digitizing the IF infrastructure. And we realized that wasn't going to happen without a digital IF standard. Analog frequencies, IF frequencies, provided a natural interoperability that's lost once you go digital, because there's lots of different ways to packet, stuff bits into a packet. But when we looked at creating the standard, we realized the other thing we realized is it wouldn't be adopted unless it was pretty simple and easy to adopt and pretty much non-threatening to the vendor community. And so that's what we really focused on with our initial DIFI digital IF standard. And we think we're doing pretty well along that first step. But we also think there's lots of other areas around the digital architected system where standards could be of value. And we'll be putting focus on those areas within the organization going forward.
Stuart, I was at your website, and the logo says it all. You don't have to speak English to understand what's going on between analog to digital. It's really talk about, making things simple. It's very simple to understand the goals of your organization. And this digital transformation sure is a term that's bandied about here in the Washington, D.C. area. Everyone's going to the cloud and making a digital transformation to this and that. People are talking about Internet of Things, the Internet of military things. So speaking of digital transformations, how will this digital transformation impact the satellite industry?
That is a great question, and it's also one that I think is kind of hard to answer because digital transformation is going to have huge impacts across the entire industry. So it's probably best way to answer that is to give a couple of examples. The first example I'll talk about is one that's already happened, And that's basically, it's enabled ground system as a service for the Earth observation market. A little of 5 to 10 years ago, if you're putting up an EO satellite, you had to consider building out your own ground infrastructure, which would require significant capital expenditure as well as recurring operations costs. But now with the availability of software modems and cloud compute capabilities, it's enabled an entire ground system as a service industry that can provide better coverage, excellent performance, and even helps get your data turned into products faster than custom-built ground systems, all for a very nominal pay-as-you-go pricing model. And they're able to do that because they're able to amortize the costs of the system across multiple satellite operators. And this has significantly changed the cost structure required to start a Earth observation satellite business. So it's really had a huge impact on that part of the industry. Another example is with respect to ground system architectures. If you look at the basic architecture of a satellite ground system at the block diagram level, it really hasn't changed much since the late 1960s. I mean, I remember I joined the industry in the mid-1980s, and I remember when I joined the industry, I was given a book that showed how ground systems were built that was from the mid-1970s. And if I pulled up that book now and I pulled out a block diagram of a satellite ground system from that book, it would look basically the same as most satellite ground systems that are being built today. And so at the architecture level, now each of those blocks have advanced massively in the last 40, 50 years. But at the block diagram architecture level, it basically looks identical. But with a digital infrastructure where you digitize once near the antenna, as close to the antenna as you can, it enables a multitude of new architectures. And as you're able to use general compute and IP routing to place your L-band plumbing and your signal processing, you can disaggregate your architecture and optimize it for the service you're providing. There's a lot more I could talk about on that topic, but let me go to a third example. And the third example is the impact on remote terminals. Right now, remote terminals are somewhat built around the modems that they integrate with. And that's because modems come from different suppliers, and they don't come in a standard size, shape, or with standard interface points. But in the future, terminals will not come with modems. What they'll come with is generic compute packages. And the modem will be a software application that can be loaded into the generic compute along with other applications. So if you think about what that means, it has dramatic impacts. So if you're the terminal supplier, it greatly simplifies your offering since you won't need a different model antenna for each modem. If you're the terminal buyer, it greatly expands your supply chain because now any terminal can be compatible with any modem. But maybe most important of all is to think about the terminal user. They can now load up any modem they need and connect the terminal to any satellite or any network that's available with that same terminal. So you consider the flexibility that creates, and then consider what if the terminal could be a flat panel antenna that could support multiple beams. That just adds a whole nother dimension of that flexibility. Or if you think about a mil-SATCOM application, where you could use the same terminal one day to support a COM-SATCOM application, and then the next day use it for a highly secure mil-SATCOM application just by loading different application software into it, because the application software could have gone from a commercial modem to a highly secure mil-SATCOM modem. So digital transformation is going to have impacts across the entire spectrum of the industry, and I think it's going to truly transform the industry and open up new applications and opportunities that we've not even begun to consider.
I'm taking notes as you're speaking. I'm writing down disaggregation unlocks flexibility. Boy, that's the summary of what you had to say. It's going to be exciting times here in the ground station industry in the next few years. Gentlemen, DIFI is a brand spanking new initiative. If you all have done an excellent job showing the benefits of DIFI and shown how standards can improve resiliency and reduce cost. I'd like to thank our guests, Lieutenant Colonel Gary Thompson, Spectrum Warfare Division, Space Systems Command, U.S. Space Force, Ben Hilburn, Head of Strategic Initiatives, Azure Spectrum Technologies at Microsoft, and Stuart Daughtridge, Chairman, Digital Intermediate Frequency Interoperability Consortium, or DIFI. Thank you, gentlemen.
Thanks for listening to Constellations, the podcast from Kratos. If you like this interview, please subscribe, tell a friend, and give us a review.